welcome to the second section in chapter 2, where we're going to delve much more deeply into logic and in reasoning. And this section is entitled Statements and Truth Values. And we'll start with that very famous question that Pontius Pilate asked Jesus when he said, "What is truth?" And it can be tricky to define what truth is. Jesus said that he is truth. He said, "I am the truth." God is truth. The Word of God is truth. But part of our job as human beings is to evaluate things that we hear, things that we see, or read, and determine, is this true or is it not? In the study of logic, a statement is a sentence that is either true or false. That's what a statement is. So it's either true or false. So I'm going to give you some sentences or equations. We're going to try to determine, is it true, is it false, or is it even a statement? Okay, the first statement I've written down on the board is the Bible is the Word of God. That is a truth statement. It's true. That's what it claims to be, and that's what it internally verifies to be as you study it. So that's a true statement. Statement number 2. People by nature are basically good. Ooh, is that true or false? People by nature are not basically good. This one is false. Here's a mathematical statement. 2 times 3 equals 9. Does 2 times 3 equal 9? No. This one is a false statement. Another mathematical statement, 8 plus 7 equals 15. That one is true. And the last one to look at is the statement x plus 5 equals 23. This is not a statement, so you cannot verify if it's true or false because it's not a complete statement until we have qualified or given a value for x. So this one is not even a statement. In the study of logic, you give statements a letter. For instance, we could, like P, it doesn't have to be P, but it could be. For example, gold is a precious metal would be that statement. It is true. Then to the negation of that statement would have this symbol in front of it. It always has the opposite truth value. So if your statement is true, its negation will be false. If your statement is false, then its negation will be true. This, by the way, is read not P. So if the statement is P, its opposite is not P. Gold is not a precious metal. Some statements have quantifiers in front of them, like a universal quantifier would be all, like all gold, or all students, or all pencils, whatever, or every square, every circle. So those would be universal quantifiers. The symbol for that is an upside down capital A. So if you see that in front of a symbol, it means all or every. Another type of quantifier is an existential quantifier. So this is when we mean some, like some squares or some circles or some people, some or there exists. So that would be some. The symbol for this is a backwards capital E. Boy, I hope you're taking good notes. And that means one or more. So when you see that symbol, it means one or more, and that's a quantifier to mean some or there exists. Let me show you some examples, see if we can make some sense out of all this. Okay, here's an example of what I mean by the statement, its negation, and its quantifiers. So our initial statement is people are sinners, and I call that statement P. So then the negation of that, not P, is people are not sinners. And then with the universal quantifier, all, remember that upside down capital A is all people are sinners. And then with the existential quantifier, which means some or there exists, some people are sinners. So all of statement P, some of statement P, not statement P, that hopefully, let me do another one. Let's do another one so you can see how this works. Here's another example of the same thing. I worded it a little bit differently so you could see how this would work. Our initial statement, now we're going to call it statement Q, and the Q statement is boys like to play baseball. So our not Q, our negation of Q, is boys do not like to play baseball. Pretty straightforward. The universal quantifier, every boy, sorry about that, likes to play baseball. I could have said all boys like to play baseball or every boy, so I worded it a little bit differently so you could see the same effect. And then our existential quantifier, which is some or there exists, or here, there exists a boy who likes to play baseball. With this one, it's one or more. So there exists one boy somewhere who likes to play baseball. Where this gets really tricky is when you're trying to negate quantified statements. Like if we want to say something about all of something and then I want to say, oh, not all, how do we negate those type of things? This is where it can get complicated. So let's walk through some of that. So here's a quantified statement. The basic statement that we're going to call R now is all roses are pink. Notice I'm not talking about whether that statement is true or false, because obviously that one's false. Just the fact that our statement is all roses are pink. So then not that, or the negation of that, by the way, since that one's false, this one should be true, because it will have the opposite truth value. One way to do that is you could say not all roses are pink. That works. Not all roses are pink. Or you could say some roses are not pink. You can also negate this statement by saying some roses are not pink. Now I've written two ways that are incorrect. If I'm trying to negate this statement, I cannot say all roses are not pink. I'm negating the pink. That is incorrect. Or no roses are pink. I can't go from all to none. I can go from all to some, but I can't say no roses are pink. This is also incorrect. Do you see what I mean? It gets a little bit trickier when you have these quantifiers. Let's try this with a statement that has an existential quantifier, a some instead of all. So it gets confusing, you guys. So I have the statement, some ladies are tall. That's a true statement. So if I want the negation of that, I'm going to come up with a correct statement that will be false. So let's look at some correct statements that would be false, that would be the negation of some ladies are tall. Okay, these are correct negations. I'm trying to negate some ladies are tall. So one is I can go from some to all. All ladies are not tall. That is not true, and it is a negation of this one. Or I could say no ladies are tall. Instead of some ladies, I can negate it with no ladies. Those are correct examples. Okay, now I've drawn or written two statements that are not correct negations of some ladies are tall. Remember that some ladies are tall is a true statement, so its negation would have to be false. This one, not all ladies are tall, is really just a restatement of this. It's not a negation of it, so that does not work. It has the same truth value. Or some ladies are not tall is also the same. Some ladies are tall, some ladies are not tall. It is also a true statement. It's not a negation of this one, so that does not work either. Those are incorrect. Okay, hopefully this little chart will be handy. It's in your book. Make sure it's in your notebooks. I have some universal statements here, some existential, some or a few statements here, and I want to show how you can do a negation of each one. So for instance, if I want to say all A are B, so the correct way to negate that would follow this arrow. Some A are not B. So I'm going to negate that all with a some. Or if I say none, no A are B, then I would negate that with some are. Some A are B. Or vice versa. If I want to say some A are not B, then I would negate that by saying no A's are B. Or some A are not B, well, all of them are. So they go back and forth. So see if that helps. And now we're going to actually try to write negation statements for some of these qualified statements. This is a tricky thing, so we're spending a few minutes with it. Okay, here's our first statement. All pies are round. So that's like all A are B. So I'm going to go down below that and negate that with, instead of all, I'm going to change to some. Some pies are not round. So there's our original statement, all pies are round, and the negation or the not P, some pies are not round. Let's do another one. Okay, now our statement that we're going to label Q. There exists a student who gets straight A's. So this is an existential quantifier. This is the sum, and maybe it's you. You could be one of those students who gets straight A's. Good for you. How would we negate this one? So there are some who get straight A's. How do we negate this? Well, to negate, if there exists at least one, then the opposite of that is there are none. So you would say no student gets straight A's. That definitely negates this. Okay, here's another universal statement. No square is a circle. So how would I negate that? If I'm saying there aren't any at all, well, then all I need is just one to negate that, right? So how about there exists a square that is a circle? There exists a square that is a circle. That would do it. So this is kind of the opposite of what we just did, isn't it? So no square is a circle. Not R is there exists a square that is a circle. Okay, the last one, because these are so tricky. This statement S, some angles are not acute, so that's an existential, a backwards E one for that. Let's negate that with an all statement. Some angles are not acute. How about all angles are acute? That would definitely be a negation of that. All angles are acute. This one is true, this one is false. Remember, that's one way to check your work. Do they have opposite truth values? Okay, we can also combine statements using either conjunctions or disjunctions. So a conjunction is just like in English, where you take two statements and you combine them with the word and. So if I want to say P and Q, each one of those represents a statement. P and Q, this is my symbol for a conjunction and. This means P and Q. In order for this to be true, both statements have to be true because I'm doing and. This and that one both. So if I say Christmas is in December and February has 31 days, that would be false. Even though Christmas is in December, February does not have 31 days. They have to both be true in order for this conjunction to be true. Okay, another way to combine statements is with a disjunction. So a disjunction is just like the word or. It's either P statement or the Q statement, either one. And this is the symbol for a disjunction for or. So if I want and, it's upside down like this. I want both of them. If I want or, then it's like a V. Make sure that's in your notes because that's hard to keep straight in your mind. Now, the truth statement of a disjunction, only one of them has to be true. They don't both have to be. It's either this one or that one. So if I go back to what I said earlier, Christmas is in December or February has 31 days, that's true. Even though February doesn't have 31 days, Christmas is in December. So at least one of my statements was true. Therefore, since it can be either one or the other, the whole thing is true. This is an example of a truth table that sometimes can help you see these relationships. And you're going to be asked to do a few truth tables. Sorry, you guys. But here's our column for our P statement. Here's our column for our Q statement. And underneath, I'm saying, is the statement true or is it false? This is what we started out with at the beginning of this section. And then this is a conjunction, P and Q. So if P is true and Q is true, then P and Q is also true. But if P is true and Q is false, then the conjunction is false because they have to both be true. Or if P is false and Q is true, still false. Or if they're both false, still false. This is a truth table to help you see that relationship. Here's another one to illustrate disjunctions when it can be one or the other. These are all the different possible combinations between my two statements, whether they're both true or both false or one of each. And then if I'm doing a disjunction, what that would mean about that combined statement. If they're both true, it's true. If either one is true, my disjunction is true. But if both are false, then it's false. So here's a compound statement. I want you or us together to determine what's the truth value of this compound statement. So the statement is some roses are red and all violets are blue. So there's my two statements. My first one is some roses are red. The second statement is all violets are blue, but this is a conjunction. It is combined with the word and. And so in order for this to be true, both of them have to be true. It is true that some roses are red, but not all violets are blue. Therefore, this compound statement is false. Here's another combined statement. This one is a disjunction or. Remember, for this one to be true, I only need one of them to be true. So let's look at our two statements. Any 3 points are collinear, or the union of opposite rays forms a right angle. The first statement, any 3 points are collinear, is not true. So these 3 points are not collinear, so that doesn't work. So that one's false. The second one, the union of opposite rays forms a right angle. Well, opposite rays are like that. Opposite rays form a straight line, not a right angle. So that one is also false. Therefore, even though that's in a disjunction with or, it's false. Sometimes you can see something like this, and it can be overwhelming. So creating a truth table might actually really help. So I have P and then in parentheses Q or not R. Yikes. There are three statements here. There's P, there's Q, and there's R. So because there's three separate statements we're dealing with, our table is going to be pretty extensive. But let me show you how you can use a truth table to figure this out. Okay, our three statements, P, Q, and R. In this one, I need not R as well. And then I have this parentheses, Q or not R. So I'm going to do a column for that. And then from there, I'm going to do P and Q or not R for the final column. And I don't know what the statements are. I know that my options are either true or false. So I just filled out the first row. If P, Q, and R are all true, then not R would be false, right? Because R, these are always the opposite truth values. And then Q or not R, which is comparing these two, would be true, because remember, for an or statement, I only need one of them, so that would also be true. And then for P and that, I did the wrong symbol here, sorry. P and this, that would be true. So there's our first row. Let me do another row. Okay, I started by just looking at my 3 basic statements and figured out all the possible combinations that I could get, since either one can be either true or false. This goes back to probability that we did before. Either they're all true, or it's true, true, false, or true, false, true, or true, false, false. Those are all the possible combinations if the first statement is true. If I make the first statement false, then it could be false, true, true, or false, true, false, or false, false, true, or false, false, false. Those are all the different combinations of truth values I can have for P and Q and R. Now from those I can build, because not R would be the opposite. This would be true, this would be false, this would be true, this would be false, true, false, true. Do you see how that makes filling out that column much easier? Now for this column, I need Q or not R. I already did this one. These are both true. These are both false. So there would be false. This one, that one's true, so this is true. This one, that one's true, so this one would be true. In this one, they're both true. This one, they're both false. And in this one, at least one of them is true. Boy, having lines across or being on lined paper would make this a lot easier for me. Okay, now that I have these truth values for Q or not R, now I can combine that with P and Q not R to see what the truth values are there. So this is true. These are both true. There's the second row. Third row, it's got to be and this one's false, so that's false. Fourth row, they're both true. Fifth row, okay, because these are false, I know all the rest will be false. So there is a truth table for those 3 statements. Now when you find out what the statements are, you can look at the possibilities. When you're asked to do a truth table, those are the steps you take to do it. The number of rows that your truth table is going to have depends on the number of statements. It's always 2 to the power of the number of statements. This one had 3 statements, so this was 2 to the power of 3. We ended up with 8 rows. If it's just 2 statements, it's 2 to the power of 2, or you'll only have 4 rows. So that kind of helps. 3 statements made this one a little bit longer. Some of what we did in these logic statements can relate to what we did in working with sets and with Venn diagrams as well. For instance, if we had the not P here, that's very similar to the complement of A. When we talked about this is our set A, the complement of A was everything that was not in A. Same idea there. When we talk about it is this P and Q, so kind of what they have in common, it's the the intersection of A and B, P and Q, so it would be similar to the intersection. If it's P or Q, that's similar to the union of A and B as illustrated with that Venn diagram. Hopefully that will help clarify some of this. I know it seems weird that you think this is math, and we're totally delving into formal logic, and that's what we're doing. That's geometry is quite different. Hopefully you really enjoy this. So that's it for this section. Do the best that you can, and I will see you guys next time.